Okay guys, welcome back. So in the last video we talked about cells in series and cells in parallel and how the relationship between those can be built using the concepts and the conditions that we have been learning so far in the series of videos on current electricity. Alright. Now what actually happens is that by if you have watched those videos, if you have not watched those videos, I invite you to watch those videos, and if you have watched those videos you might have learned that most of the circuits, or most of the loops, or most of the apparatus that we have been using so far in this series of videos on current electricity have been always in a manner, right? Always in a manner so that we can simply use this, simplify it into a simpler circuit. Now, say if you get a circuit like this, you get a simple circuit like this. Simple circuit. So this was from one of my previous videos. So if you simplify, you can easily simplify this circuit into its resultant value of REF, right? Or the effective resistance, which we found to be some value, right? Which we found to be some value, but 4 ohms in this circuit. The resistance to be 4 ohms. So what actually we did was we simplified the whole set of resistors into one circuit through the effective resistance, and then given the voltage we found the current, or given the current we found the voltage. And in the last 3 videos before the last, we found a new theorem in which we found the electromotive force as well. Electromotive force. So what actually happens is that we found the electromotive force, and then we found a new theorem in which we found a relationship between the voltage and the current, and also the internal resistance. So those theories can be applied to circuits in which we can easily simplify it, and in which we can easily get a simpler equation or a simpler solution using the problem that we have been given. But all electric networks or all electric circuits cannot be reduced to simple series or parallel combinations. So what actually happens is that if you were given some combination, or if you were given some circuit, or if you were given some apparatus, or if you were given some loop or something like that, that cannot be reduced, we have to take another theorem into account, or we have to learn and we have to apply that theorem in order to find the solution for the problem. So for those relationships, a new theorem called Kirchhoff rules have been introduced, and that is the basis of this video. So I'll be talking about Kirchhoff's rules in this video, and there are actually two rules of Kirchhoff's rules. There are two rules. The first rule, or the first Kirchhoff law, is popularly called the junction rule, is about the conservation of charge, and the second rule, which is popularly called the loop rule, is an observation, or is a rule that obeys the conservation of energy. So let's see as to how these conserve the charge, and how these conserve the energy, and what are the rules and how we can apply those rules. So Kirchhoff's rules, as I mentioned in the last video when I was talking about the combinations of cells, there are actually, in my preference, as I see, there are two main relationships, or there are two main theories that you need to understand in order to understand the concepts of current electricity. One is the effective resistance of a circuit, and the other is the Kirchhoff rules. So effective resistance of a circuit was described earlier in one of the previous videos and a series of videos, and in this video I will be talking about the second and the most important concept in current electricity, which is the concept of Kirchhoff rules. So Kirchhoff rules, as I mentioned earlier, is used in instances in which we can reduce circuits or any other loops or anything, or electric networks, to simple series parallel combinations, or series networks, parallel networks, or series parallel combinations, mix of that. So Kirchhoff rules are used for that. So let me introduce the first rule, Kirchhoff. So today's topic is Kirchhoff's rules. Kirchhoff's rules, right? Rules. So as I mentioned earlier, there are two rules that Kirchhoff introduced to current electricity, two main rules. So the first rule is popularly called the junction rule. First rule which is also called the junction law or the junction rule, because it explains to you about what happens when current comes to a junction and goes away from a junction. So the first rule is like that. It says that the algebraic sum of the summation of the currents at a junction is 0. Now that's a little bit complex. What actually happens is that the current or the algebraic sum of the currents at a junction. Now, if I take a junction to be like this, and if I have a current of 5 amperes here, current of 6 amperes here, and a current of say some ampere, and take it as now, right? Simply like this. What actually happens is that if this circuit obeys these Kirchhoff rules, any circuit obeys Kirchhoff rules. So what actually happens is that according to the first rule, the junction rule, the total current or the algebraic sum of the currents at this junction should be 0. So what actually happens is that the total current in this direction is 11 amperes. So this is I, but current is normally, as we take it as a scalar, but if you take the voltage sometimes we take it as a vector, but normally the voltage is also scalar. But when you are calculating, actually we are not taking it as vectors or scalars. We actually, what we do is we are taking it into like the displacement is a scalar, but in some instances we take the current in which this, if it is going in some direction, to be positive and the other direction to be negative, and the voltage to be positive and negative according to the laws. But you should not confuse that the current and voltages are not velocity, not vectors, right? They are not vectors, but we normally take a sign complement or sign configuration in order to find the solutions, right? That doesn't mean that these are vectors. All right. So according to the junction rule, the current at the algebraic sum of the currents at a junction is 0. So the algebraic sum of the currents at a junction is 0 means 11 minus I should be 0. So I should be 11. Right? So this is also similar to this one. Sometimes we get a simply this one like this, 6A. So that's why I mentioned that the current is not a vector. If I get I here, I is again 11, right? 11 amperes. So that is also means that the current is 0, right? So what actually happens is that when you get some current at a junction, when you get it from one or two ways, so if you have simply a junction like this, in which you get 12 amperes here, so the current will flow again, the algebraic sum should be 0, right? So that is the reason, so that is the meaning of Kirchhoff's rule, or the Kirchhoff's first rule, and that's about the junction rule. So the second rule is again, okay, before explaining about the second rule, so as I mentioned in the first part of this video, the first rule of the junction rule is also popularly called an application of conservation of charge. Now you know that I is equal to the derivation of Q over time. I equals dq by dt. So if I is conserved, what actually happens is that the total algebraic sum of the current at a junction is 0 means what actually happens is that what you can say is I is conserved. So this is simply like the conservation of energy, conservation of linear momentum, conservation of rotational momentum, right, or angular momentum. So this is also like that. I is conserved, right? Conservation, I is conserved. Right? I is conserved. So I is conserved means dq by dt is conserved, because I is equal to dq by dt. So this factor is conserved. So time is independent of anything. So we don't take the effect of relativity here. So we take time to be an independent one. So if this is conserved, q should be conserved. Q should be conserved means q is conserved means this obeys right. So this obeys, what actually happens is this system obeys the conservation of charges. Conservation of charge, or charge conservation. So this obeys the conservation of charge. So what actually happens is that at the junction rule, the total algebraic sum of the points is 0, right? The total algebraic current around that point is 0, and then what you can find is that this obeys the conservation of charge. Alright. So the next law about Kirchhoff's laws is about the conservation of energy. So let's see how the second rule explains as to how the energy is conserved. Alright. So the second rule or the second law is also popularly called the loop rule. The loop rule, because it's talking about loops. Alright, so what is the loop rule and how does the loop rule help us to build up a relationship between the current and the other stuff? Okay, the second rule is like this. The second rule says it is again about the algebraic sum of something. So the first rule says the algebraic sum of the current at a junction is 0, so that's the junction rule. In this rule it says that the algebraic sum of the changes of the potential around any loop is 0. So in the first law we have been taught about what happens at a junction. In the second law we discuss what happens at a loop, right? Inside a loop. So that's why it's called the loop, popularly called the loop rule. So it says that the algebraic sum of the changes of potential around any loop is 0. So that means if you have some loop like this, I'll take some dry cell of electromotive force E and its resistance is R, right? E and R, like this, and another resistor here of resistance R, simple capital R, and this connected into like this, and this connected to voltage load. And I'll take the current's direction to be something like this, from the positive end to the negative end. So what actually happens as we learn from the circuit notation or the circuit definition or circuit configuration, as we learn, what actually happens is that the total now as the Kirchhoff's second rule explains, the algebraic sum of the changes of potential around any loop is 0. So what are the changes that happen to the potential when you send a current like this? So one is the change of potential around this one. So that is actually equal to E, and the change of potential due to the resistance which is IR, and the change of potential due to this one I take as V2, which is V1, right? V1, which is I times capital R. So these are the changes of potential that you will experience when you connect a simple apparatus or simple loop like this. So Kirchhoff's law says that the algebraic sum of the loops, right? Algebraic sum of these is 0. So what actually happens is that you will get E equals E, and if I put the Kirchhoff's laws in some direction, so in this direction, when you are putting, so if it is from the negative loop to the positive loop, what actually happens is that it is when you put that, it is negative, right? So it is negative. So what actually happens is that you have to subtract IR. In this direction is close positive. IR is 0. So E is equal to I R minus 1. Right? So that's a simple thing you can get from here. Right? So in order to put the loop rule, what you actually have to do is you have to take some direction. So if you take this direction instead of this direction, if you take this direction, right, this direction, if you are putting, say this is the loop of ABCD, so if you put in the direction of ABCD, or ABCDA, right, ABCDA, what actually happens is that you have to subtract now. If you are there, you have to add this one, IR minus IR is 0. So what actually happens that E is equal to I minus, right? Oops, sorry. Yeah, that's true. Alright. So that's the way you get. So the how does this second rule or the loop rule, Kirchhoff's second rule, become a conservation of energy? Alright, conservation of energy. How is the energy conserved? Alright. So how is the energy conserved is a matter that you have to understand. That's what happens when you're selecting some loop like this. So the total potential around this point is 0. So the total potential is 0. So if the total potential is 0 means the potential is conserved, right? The potential is conserved, right? The potential is conserved. So what actually happens is that if the potential is conserved, you know that if V is conserved, right? If V is conserved, what it actually happens is that V squared R is conserved. So the total energy should be conserved. So total energy should be conserved. So for the total energy to be conserved, what actually happens is that the total potential or the total potential difference should be conserved. So the second rule is about an apparatus, about theory about the conservation of energy, and the second rule says that the algebraic sum of the changes of potential around any loop is 0. So that's about the Kirchhoff's laws. So in this video I talked about Kirchhoff's laws. So I think you get many important information from the theories I have discussed so far about Kirchhoff's rules. So Kirchhoff's rules, as I mentioned in the first part of this video, are of extreme importance if you are going to study current electricity, because Kirchhoff's rules are used widely in many applications, not even in the basic current but also in many applications like even potentiometers and everything. You find that potentiometers, Wheatstone bridge and the meter bridge or something like that. So you have to use all that, right? You have to use it all there. So you have to find how the current varies and so on. So those actually very complex theories, but I will not discuss those here. What actually happens is that it is very important, right? Kirchhoff's rules are very important. So there are two, to summarize this video, there are two rules of Kirchhoff's rules. The first rule, which is also called the junction rule, is about the conservation of current and hence the conservation of charge. And the second rule is about the loop rule, also called the loop rule, is about the conservation of potential, hence the conservation of energy. See you next time with a new concept on current electricity.